Hey guys. All right. So you caught me over here. Let's see if we can get some action going here. We're going to talk about uniformity, loading, equilibrium. Let's see if I can share my screen now. And we'll go from there. So I should be sharing my screen with you. Let me make sure that's off. Cool. It is. Hey Brett. Hey Brett, if you're there, hello. If you're a new guy, just a new person just hopped in. Hello, hello. Okay. Let's go ahead and jump into what I'm talking to. I'm waiting for a couple of people, I guess. Hello, hello. Let me just say hello to everyone. Hello, anyone and everyone. All right. So creep. I should have some definitions open for you. Here are the plans for FIU, the bridge structure. You know what? I should grab my mic. It acts up, so I'll just do it this way. I'll just talk up loud. So these are the plans, 2017 and 2018 plans. I'm going to hit on a couple of things for you, but right now, let's jump to, you ever wonder how the steps work, for example? How does this work? It's the deflection between here and here that you're trying to defeat with the load, the anticipated load in the center. So you don't want to see deflection here. You pin, sometimes it's pinned here, sometimes it's not pinned, meaning allowing for movement. This bridge had steel stays. Let's go to the top. Let's go to the top here. This bridge had designed in steel. These guys here are made of steel. They were pipes. They are pipes. P-I-P-E-S, pipes, literally steel. And if you notice, they're not uniformed. If you can see, these angles aren't uniform. They meet by force angled because one is this distance is 175 and this one's like 100 feet. So they divide up the distance roughly to give this look, and it's supposed to be lighted. Now the video I'm making is about equilibrium. So equilibrium is one of my favorite words. One of my favorite words for almost everything. You tell me you're in an argument with somebody, well, you're at equilibrium. Figure out what's wrong with equilibrium. Once you're in equilibrium, once things are in equilibrium, they're static. They're okay now. Nothing's going to act on them. You're okay. So this was not in equilibrium at the time of the failure. And so you would find, well, what was out of equilibrium? Well, we know that, let's just jump into a couple of tabs here. This was out of equilibrium. And yet these engineers, all of them, decided that we can disregard equilibrium and we can just use, financial reasons to keep on going, because any engineer evaluating this, let's use Denny Pate specifically and Linda Figg's company. Let's use them specifically. If I hired them to evaluate this structure here, they wouldn't say, "Oh, you're good to go. Go ahead." No, I don't see anything wrong there. With a quick 2-hour meeting, they wouldn't say in 2 hours later, "Oh no, that's nothing. That's nothing. You go ahead. You're okay. Go ahead. No problems." So therefore, it was a financial decision to do this because it clearly is not an engineering decision to do this. Nobody in 2 hours would say this is an equilibrium. Equilibrium is one of my favorite words. Like I said, I've actually changed my other channel to add the word equilibrium to it. I don't know why I didn't think of doing that before. I think because I had photography in it mostly. So now look at this design, and we're going to think about equilibrium again. I'll see any comments in a moment you're making. As you look at this design, does this look like it's an equilibrium, this design? I initially did a video on this, maybe about my third video out, and then I blocked it because I had many people who wrote me on the side, even tell me they're engineers and my logic just sucks. And I said, you know what? I felt like I can get in trouble at that point with some of my comments. And so I decided to block that video because it was a little too advanced for that conversation and it could count against me engineering wise. But after we get the photographs back and everything else, that video turns out to nail it. That the pattern, this pattern it was just nuts. It's not a typical load sharing pattern where you get reversals. This is, in my opinion, as I was saying, mostly designed to under post tensioning to take all these loads, and this is more decorative. Exactly what it turned out to be. That this was not really, it's not really designed to take loads. This layout, I couldn't figure out how it was designed that way either. With that said, these pipes are steel, 16-inch round, and they have a substantial amount of weight on them. We're talking about inclined weight here. So this is an incline. And you're looking for uniformly loading. If we would take, and I'm going to be real rough on this. I'm not going to give you any formulas because why? I mean, maybe I will when I say I don't. When I'm not, since it's live, who knows with me? But I'll try not to give you any formulas. I'll just dumb it down so even I can understand it. How's that? So if you would take half of this down the middle from here to here, you theoretically say the other half is on here. This half here, it transferred to this column, this pier, and then this is transferred down here. If you were to remove this piece of steel pipe, you would see that, well, it would put a leaning, a torque, a leaning, it would put tension on this column at this point, pushing away, pushing away here to the right. I'm not going to say y-axis, x-axis. We're just going to say to the right because some people don't know what y, x, and all that other stuff is. So I'm not going to confuse it. I'm not going to talk about positive rotation or negative rotation. That's for engineers. If you guys are engineers, well, then you can write down there. You should have said positive, negative, and rotations. Where's this for the general public? So anybody engineer here gets triggered by my common talk, then I apologize for triggering you. So down the middle here, so we're going to take roughly this part. Now, if you don't have this on here, it could push this over. Imagine all that weight leaning at the top of this concrete. It puts this part in compression, this part in tension, and that's that. Now, the counter, the equilibrium part of this, putting it back, is this part, putting it back in equilibrium. So these two are trying to cancel each other out, except for they're not, because they're in different angles. This angle here and this angle here are not the same. They're different angles. This angle and this angle are different. So the equilibrium's off. So to counter for equilibrium, you have to increase your sizing, lower your weight. You have to do something to counter for it. I saw nothing in all the math that I've saw on this, and the math that I was able to get from my disclosure. I saw nothing nothing in clear language saying that this is designed to counter, make this have equilibrium. With that said, let's just go on with dead weight. This is dead weight. It's not structural except for the point that it was supposed to help with resonance, wind blowing with the bridge to keep it stable. And I would guess that would just be because of uplift. And well, I'd have to add uplift because uplift does exist, and this would be resisting uplift. At the bolts, though, at the maximum capacity of the bolts and the downward weight of these steel members. With that said, you take this half, that half, that half, that half, that half, you add up all that steel weight, and you then can transfer more of that steel weight onto these blister bars, they call them. You transfer it on there, that's a downward force. Now, I was going to do a video showing a weight, and I will do it, showing equilibrium, how crack foundations work. I'm going to do a lot of it, little stuff like that. I'm getting a lot of side comments that I'm not posting, but people want to know about crack foundations and how that, how to evaluate. So I'm going to do a lot of videos on cracked foundations, and it's going to be very easy for you guys to understand cracked foundations and how they, how it came about, and leaning foundations. So now let me write down something here. Now that I said it on the video, I better write it down and make sure I do it. All right. So yeah. All right. There we go. So now this is dead weight on this blister bar. This blister bar has an anchoring, a bolt, so they tie it down with. That dead weight is a lot of weight that's on top of these guys. That dead weight is countered by post-tensioning. As you can see, dot, 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 dot. I believe that's going to be their post-tensioning lines. and or something close to it. Future bridge to parking. Okay, we won't bother with that. Let's go to, there's a diagram again on a scaled program. Now you can use this, and you could see that these boxes are square. So if you were doing like a map of something and you wanted to figure this out, you can use these boxes real quick. If you're doing navigation, on my other channel, I'm doing gravity and all that, having a little fun with gravity, and I think it's really equilibrium. Gravity, I just don't get. Equilibrium, I get. Gravity, no, you can't tell me it's pulling up oceans, but it can't even pull an atom. I got to use NASA because that's going to be my biggest supporter of the counter statements against me. So using NASA, it says it can't even pull an atom. If that's the case, how can it pull a darn ocean up? But I digress on the wrong video. If you look at this, back to mapping, this bottom line dissects right at the bottom corner and almost dissects at the very top. There, if it did, and this being a square, you could say that's a 45-degree angle. So if I was at this location to get to this exact location, I would say take a due course of 45 degrees north. If this was north and that's south, northwest. And if it's 22.5, I would say northwest, which would put it 22.5, or north west north, 22.5, the other direction, this direction. So now, yeah, it doesn't work the other way. I tried to make it work. Anyway, I think I just messed that last part up. So there's that. Now looking at this, you would say the counterpart for this one, if I said this one is 45 roughly, it's almost at the corner, not quite there. It's the outer member, and as I slide over the outer member, well, that's not the same. That doesn't meet at the same, doesn't cross in the same equilibrium path, if you will. The forces are different. If I go left to right, not just these two contact point here or here, but here to here. There's nothing equal about this. The closest to equal is these first two guys in here. They're the closest to equal using these boxes and the scaled drawing. They are the closest. See that little triangle here and with the triangle there? Push it over a little bit and you'd have been equal. So you can, I'm just showing you how you can look at plans real quickly and go, look at it and let your common sense of equilibrium pop up and go, I don't see equilibrium here. Once you don't see it, you need to bring that to your mind immediately, write notes saying, I need to question, how is this balanced? Because balance is very important in all of engineering. I just can't do anything I want. Everything has a limit. And so if I do an overhang, for example, here, how is it balanced? Well, the equilibrium of this overhang based on the live loads predicted, the 50 pounds plus a dead load, is countered by the engineering of the floor deck. Or if it was being held by the top and then this is a brace holding it from the bottom up, like a hanger, well, then it would be countered by the roof deck, if that was something you so wanted to engineer to do it in reverse. Let's go to, so bear with the screen. Sorry about that, it is live. And let me see if anybody's here saying hello. And I got here, hey, hello. Oh, nope, that's me. Hey, Bruce. Bruce, my cat's name is Bruce now. I named him after Bruce Lee. I wanted to name him Einstein because he's so smart, but my girlie said no to Einstein. I want to show you physics lab, something on forces acting at an angle. I just want to show, I have to critique this to show it. So I'm critiquing it. It's not showing up. I wonder what's wrong with their website. All right, now I said that. You guys can go here and see if you can figure out, wink, wink, what's wrong with their website. This will help you, lead you towards forces acting on an angle, which I'm talking about. Let's get rid of that. So this is forces acting on an angle. It's the same thing, this cracked member. So if you want to find out about the cracked member, start studying forces on an angle, and you'll start understanding how it transfers. And sometimes they switch off on loads. They're not always on the compression. Let's give you an idea of that. So you cross, where's that bridge? I think it's, So when someone tells you that this is under compression, that's under tension, and it really irritated me. This is compression, that's tension, compression, tension, compression, tension. That triggered me a bit, because I'm like, clearly you're not really a structural person, because it's reversals too. If this is in compression at this point, well, if I take the same load from this point, I move it over to here now, this is now a downward force, putting this under tension a bit. It is transferring its way back down, but it's also doing a little bit of both. It's just not under compression only. It still forces down the bottom that's being acting upon, that's acting in a pulling motion, if you will, a pulling down motion. And you could say it's gravity. I just say it's the forces trying to find equilibrium. What did I want to show you here? I'm not sure. I think it's just some photographs. Going back to this guy here. So I did mention creep. Let me show you creep. I want to use this definition of creep. Creep. In material science, creep, sometimes called cold flow, is the tendency of a solid material to move slowly or deform permanently under the influence of mechanical stresses. So if I lean on you right now with my body, you like, oh, it's kind of cute maybe for a second. And as I keep leaning on you, all of a sudden you can't take the forces anymore. They build up. The same amount of force, but now it's building up in you. Now it's like, oh, now you're like, hey, get off me. It's too much weight. For a second, you could take it, then you can't take it any longer. Creep is, just think of it like that. But creep is really, I put a 100-pound weight on a table, and it deflects just a little bit, let's call it. And then I'll leave it. I come back, 20 years later, and that little bit of deflection now, and I got this nice, beautiful bow in the table. Nice, beautiful bow. Went from that little teeny bit to a giant bow. That is creep. Specifically, I can show creep in a lot of places in a city on the brick walls. You'll see brick walls leaning out, things like that. The person didn't design it that way. Over years, it creeped out. It could be everything from the foundation to they put it at a plumb. And it's already, in the forces of being at a plumb, it's leaning away, can start your creep. It puts the inside of the brick in tension, compression, the outside in tension, and you just need some forces to help accelerate that. But mostly it's foundation. So that's creep. Mostly it's foundation and not the walls. Depending on wall build design. Okay. Yeah, I want to do a video on that creep, on what I just said on the wall, because I can show some creep in the walls, and it's awesome because I can show a solid foundation, and I can show the wall being out. It's underneath a windowsill. I think I know I have a job site I can show that in. Let me find these columns. The steel beams, and that's about the size. So here's what the Christmas tree looks like. That's your center point of the Christmas tree, and these angles they're not balanced. They're all over the place. So there's your imbalance. This is balanced. Their post-tension angle was mostly balanced. It did some weird numbers, but left, right, left, right, left, right. All in balance. All had equilibrium. As far as I recall, they all had equilibrium. Now, equilibrium can be thrown out by you not, staying within tolerances. But it was created with equilibrium. The left side is equal to the right side here. In fact, when you see the drawings, they'll usually refer to it as it'll show one half of the drawing. The other half is exactly the same. There's no reason to show the other half. Here's both sides. As you look left and right, this is equilibrium. Equilibrium. It's a beautiful word. Again, you got a bad relationship, you're out of equilibrium. Maybe you're the one that's out of equilibrium. Maybe not. Maybe it's the other partner. Your center lines, equilibrium. Okay. Let's scroll down here. You're mixing your concrete PSIs on the same job site. Let them butt up against each other. Equilibrium problems. This was interesting on an equilibrium problem standpoint. This is this was something was brought up by and I put in one of my videos, the other channel, brought up by in the meeting with Linda Figg and Denny Pate. It was brought up by one of the people of the board that was questioning about the plans. And somebody came up with a simple question based on equilibrium. These steps are 16 feet wide. These are much larger. This would allow for more people to come up and get onto this deck more so than the one with the smaller steps on the opposite side. It was a size difference of it was a nice significant size difference, and it was so simple. It was so simple. Their argument was basically the school gets the prettier side, but the township side, if you will, they basically didn't have the money to do the fancy steps, so they don't get the fancy steps. They got the squared up diagonal steps, if you will. And the Sweetwater, I mean, the city of FIU got the pretty side. So let me show you. Let's get to that. Let's get to that those steel beams, and then I'll probably be able to terminate the video after that. Pretty much. I like to stumble across the step deal to show the two widths. The two widths of them. Landing. 10-foot landing. I don't think it was the landing that was an issue. It was bottlenecking though, and I was like, yeah, there's bottlenecking. Okay, it's this side. This side is, so the other side was what, 16 feet? That's elevation. Or is that a station? No, that's a station. That's a station. 12 plus 5, 5608. Stations are surveying when you, it's the location, so that's not the, it's not an elevation, my fault. Well, looks like there it is, 11'2" outside the outside. And elevation, electrical room. It didn't quite say stairs, did it? Yeah, center line of stairs, 11'2", 22, so the outside, bicycle track, 3.6. I think that might be the bicycle track. But anyway, the steps are still out of equilibrium from one side to the other. And I was like, you know, they're right. Theoretically, they race up on one side, then they bottleneck trying to get off the other side, and they're backing up. And you got all this dead load on the structure, you know, just piling up while people at these football games is what I would theorize they're talking about. And it was just so stupid or so silly. And there it is again. I think that's the steps. You guys can research that yourself. But it made sense to me. Now back to the pipes. Here are the pipes being held by these. These are pinned. So these being pinned, as the bridge, this would no longer allow for expansion and contraction without some damage being taken place. It's not a flexible joint. These are pinned, 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 P-I-N-N-E-D, I-D-E-E-D-E-D. No, I'm just kidding. Bolted down. So this now allows for no expansion and contraction between these locations for sure, without failure happening. So I find that interesting that they pinned him with no, I didn't see any detail that showed anything fancy. These are your post-tensioning. These are the post-tensioning marks, if you guys want to know. So you're looking at 1, 2, 3, 4. This is section BB. Section BB would be, that's section A, D, E, BB right here. So that's 1, 2, 3, 4. Oh, it's marked 8. So it's this guy right here. So number 8 has 4 post-tension members going down it, symmetrically like that. Number G is our failure one. G is the failure one. That's the one that is very clear on failure. And there's a 2 bars, 1 and 2, 1 and 3/4 inch post-tension bars and duct, typical. And duct. That means the tubes that run down. I don't think we did see the duct, right? And number 10 is FF, Frank, Foxtrot, 1, 2, 3, 4. And the post-tensioning energies are different. So GG and FF, they receive different tensioning. For example, FF, not for example, but let's see. Okay, so it's not clear right there. It's somewhere else. So you can see the way that bar, they and they had the steel pins going here for the pins here, I believe, and here are the pins here for the 1, 2, 3, 4 for the and they're not sticking out at this point for the steel columns to rest on there, those steel decorative piers. This is a profile of the blister bar. So if you can imagine, this is looking at it from the end of the bridge, this is the profile. It goes over further. This little break in the line means it continues. Well, normally you do a break in the line this way, but they did a break in the line this way. So I get it. It continues on left and right as we're looking at it. You see the symmetrical location, symmetrical, and there is your equilibrium I'm referring to. Here are the pipes now. Now the pipes are non-symmetrical, and the degrees, etc. There's nothing. Okay, so we're on the smaller short section. This is 196 feet long. One to the far right, I thought they gave the angle here. I recall seeing an angle. And just looking at symmetry, you look at things here, 6 inches, 6 3/4. So this is a profile that's being created when you read this. Whatever this 6 3/4 and here's 7 3/4, they're different. That's 6 and that's 5 3/4. So it's getting closer and smaller numbers as we get closer to the column. Perhaps that will create some symmetry, but I doubt it. Now, there's the symmetry they're looking for, dead center loading. Isn't it interesting that there's dead center loading of all these columns, but yet the structure underneath is not the same? So how can you design everything the same, but put this dead center, and now it's offset of this much. Now it's almost on top of it, and at this point it's almost on top again. This one now is on top, splitting a difference. So if anything, this load looks like it's going to be a downward force. Not in line, but maybe it will be if it was pulling down at this point. Maybe it would then put those pins under stress and then put the pier under stress, in a tension format. I mean, when I say under stress, but you lose your symmetry, and if you do, then you would now bring up the conversation of, well, how did you? I see the location of this. How did you offset it, or is this a non-starter? Is this just so light in weight, the steel, compared to what your structure, it's not going to deflect it, but you'd have to add on all of these together at these point loads. So these are called point loads. It matters where your point load is. So if I put my arm out straight next to me and I give you 10 pounds to hold in your far right hand, you're not going to be able to hold it as much if I give the same weight and now I put it near your shoulder. You're now going to be the right hand now has become irrelevant almost, even though it's sticking out. But yet I still put it on the same arm, but I put it closer to the shoulder. You see the difference there? So now these point loads do matter. Usually, typically, the weakest point in any span is the center line. Under deflection, under shear, it normally would be by the supports here and here. Shear can can change though, because then these are new points of shear. Right here is this, as the forces of the weight of this item, the steel pipe is in a downward momentum, that this becomes a shear point right here. This shear point becomes here. The plate distributes the load off of this, so your shear point, in theory, your shear point would change as long as the plate doesn't deflect. It's designed not to deflect on those loads. It would then transfer out to the edge of the plate, and that means you divide all that load per the square inches of the plate of the kips of the PSI, not PSI, of the dead load weight. So if it weighed 10,000 pounds and your plate covered an area of 24 square inches, 24 times 24, you divide that by that 10,000, and now you know what the loads are on this. And then you would try to figure out whether this could take that load with no issues. So you would say, okay, this is not going to cause any deflection. Then of course you would add in this load now transferring down here. But again, that's this entire plate. So if you were theoretically going to do it, you would say, well, the part that this is affected by the transferring, even though it's on an angle, I would still say somewhere about Now, I'm not counting that little 8-inch part probably right there. I would go up like this and say, huh, it's right on the edge. It's right on the edge. You couldn't put it in my theoretical fast answer. I would say you couldn't have put it in a worse place. Over here would have been better. Putting it, you're actually directing it, just good shot right down the edge, right down the weakest point. That this doesn't count. So that you get the blister bar thickness in this. And then you go, oh, well, the blister bar is now part of the formula. So now the shear points might go out to the end of the blister bar based on the thickness of this blister bar, puts it out here. So now I go, huh. So if the load is here and the blister bar transfers it, that puts the load back to here, if you follow that. And I go, well, now it's got a substantial amount of this load transferring down this column. On the back side of this column, splitting it half and half, that's the center line. I would say over here, not so much. No. Now I'm at a cantilever of the same load. And now I need to know at what point will this fail, this section from here to here. Because I would then say the loads transfer down here. This is on an angle, and I'd give it the angle. I would say the loads transfer down to here. And I could argue with myself that they would stop here. But I'm a 45-degree man. I like when it's 45 degrees. I like the loads transferring all the way down at 45. I'm a believer in that, with the exception of bolts that don't like my 45-degree rule. Bolts like a cone shape, and it's not 45. It's less than that. And I think in one of my videos I kept showing 45 with the bolts. I don't want to take it back, but I do want to take it back and say I should have made sure I mentioned the cone as part of my video commentary and the other ones, that it doesn't like my 45-degree angle. That's based on current engineering testing. And these are mostly bulk companies and things like that do that testing. They give the data. The data gets accepted, and you run with it. It's not engineers doing that. I mean, maybe they're engineers, but usually it's not. It's just testing labs that figured out failures and influences, and they say, there you go. All right, I'm gonna try to see if I can scroll to. I'm gonna look for your comments in a minute, but if there's any there. I want to. These are the blister bars. Well, I'm not sure of that. I want to grab the. It was more on the columns. I'm going to see if we can find them real quickly. This is the structure. This is what they call a profile. This is the post-tensioning members, the cables that come across. They just don't go straight across. This is the top looking down, like we were a bird flying over and froze and looked down. We would see that this member, that last pocket, for example, duct, goes straight. And then about this point, it jogs over and ties off here. This is the 100-foot, 91 feet distance there, and we saw 96 a moment ago. So you keep that in mind if you're so inclined to. Here's WP. This is the pipe, and there's our connections again. And you can see they center line the plate, but not the pipe. The pipe looks like it's supposed to be in line with the column. The plate is not. So again, remember I said about deflection. So ideally and in balance. So I would pick this distance here, come to this distance and say, okay, that's fair game. Now this part is overhang. So I want to know how much what would cause this deflect? What would cause to balance a 6-inch overhang of 7502, whatever kind of steel it is, to deflect? And it might say you need 100,000 pounds to deflect it by 360 or whatever. So you go, oh no, that's fair game. All of it counts as a single plate, irrespective of this little bit. Meaning it doesn't matter that you added that little bit. Back to the profile. So these are the two that were installed. These were yet to be installed. And I'm trying to verify in my brain. Yeah, these were yet to be installed. This is the 175 foot and some change. These two are going to be installed through both bridge tops, both bridge decks. The last two, the one here and the one here. I thought there was 4. I'm only seeing 2. 4. 1, 2, 3, 4. There were total 4. These are 2017 plans. total of 4. One moment. Bear with me, ladies and gentlemen. With a total of, okay, right here. I think that might be a little too far for me. These are the anchors for that, what I'm talking about, these plates. And that's that shape. And here are the anchors that shoot up. Looks like you did a little grinding on that, huh? I'm looking for the end of the bridge structure. Might be in this other tab. Right here is when it's the other end is standing up. It makes it very clear and easy to observe that end. So bear with my little self. Oops. Got a video coming up on bearings too. Changed it on my one vehicle. And so I ran into a problem with manufacturers. Timken is not who they say they are. They use a lot of Japanese stuff. Give me something to talking to. Not Japanese. They market out to a bunch of people, apparently, because the quality has really gone down in Timken. And tons of reviews on that stuff. My end comment would be, buy from the dealer when you're dealing with bearings. Yeah, you're going to pay 100 plus, $80 more probably per bearing. Come on. I want to show you the end. I'm still looking for the end. Right here is what I'm looking for. 1, 2. Okay, so a total of 4. 1, 2, 3, 4. Now, that's legit. So there's my 4. I got my 4 in my brain now. So let's go back to that one. Hey, Tom. Tom, AS. Hello, AS. Tom and AS. Hello, hello. So back to, so here's the 1, 2, 3, 4. So this is the profile. So as you can imagine, when you post tension this, it's not a straight line. This creates a bending moment, a torque here and a torque here, and then your straight line. This is symmetric, half the bridge. So the other half would flip around and do that. Although the nodes, wait a minute. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So it's this is oh, I see the split now. I didn't see it. Yeah, they continue it. All right, so yeah, so that's the tendon, and on the one end it straightens back up. I thought it definitely. I apologize to anybody seen my previous video because I said that this was profile matched on the other side. I'm totally. Wait a minute. 175. Pylon right here, center line. Yeah. So anybody keeping track of my videos on the other channel? This is I did that. I stated wrong because I recall me stating that, or something in nature saying this would be the same on the other end. We are looking at the other end. So they were straight here. The profile jogged in. So these two are active at this point. When they're active like that and they're pulling taut, tendon 2 and tendon 3 right there. See tendon C3? This is canopy 3 and I believe C for canopy, and canopy 2. These, when you pull them tight like a string, remember they also, since they go around these curves, they create a torque right here, left and right. So put a thumb here and a finger here, your index finger here, and then imagine trying to do it clockwise as we're looking at the screen. It creates that torque. So a torquing action, pulling the forces, compression inwards, 1 and 2. They all line up like that, together. Symmetrical, not these two are not symmetrical, but they're symmetrical in that their spacing is equal. Now this is the bottom deck, tendon D. This is the deck. These guys look like straight shots. See them? Straight shots. This is what made me think that this deck in the initial videos I started making under 2016 drawings, not the 2017. That I said, well, perhaps they designed this so all the loads could be taken on this, on the resisted by the tendons in the lower deck only. And it didn't matter that all the upper weight was and the tendons weren't complete. This was designed to counter all of those weights. That's what I said, but then I found out to be, not true. That they just didn't care. They were more concerned about money. Because remember, you just jump in this video, as I stated, represents stressing and anchor, represents non-stressing and anchor. So this is where you would put your connection and start pulling your cable through. They both experience forces. Same thing here, and same thing here. And this would be the pylon right here. So you wouldn't have this there. You couldn't tension again once the pylon's in. You're toast. You couldn't do it. So you see why they're outside there. That's that part that stood up on the pedestal. That was okay, if you will, number 1 and number 2 section of the structure. Here are your tendon profiles. We went through this in another video, but now they're different because I have the disclosure of this stuff. Here is the what I was referring to, the pipes, these direction of stationing. So this looks nice, right? It's got some little weird shemity going on. This nice little design, but this is the failure section. 16-inch diameter round pipe, center line of steel. So working point. This is where you're going to measure from and secure from. And then you're going to secure it to the column up here, as you can see. And this, again, this is my symmetry issue, my equilibrium problem. That's what I wanted to show you. I wanted to get you to this. Where'd it go? I went too fast. To this page here. Now, I'll give you a copy of these drawings right here. Let me copy it. And let me drop it over here now for anybody interested in jumping back in there and taking a peek at it. So there you are, Denny Page signed and sealed drawings. This is from FDOT. So remember, FDOT they're responsible, but I got another video coming up showing that I'm going to show that. Well, I hate to give away my teaser already, but the teaser is I'm going to show you FIU is responsible. And it's funny that so the government the OSHA can ticket governmental organizations. You can find where they ticket governmental organizations for violating rules. OSHA does. But why they give FIU a pass on this, I just find this just like non-rational. FIU got a pass on it. I'm going to show you. I don't want to give it away yet. You got to wait. I'll give it away to you guys listening right now. I'm going to do a video showing that what I've been waiting for forever. I finally got the disclosure in, showing that FIU had the permit. They did issue a permit for this bridge construction. So they are the ones that should have closed the road down, and yet they got a free pass. FIU is a private organization, right? They're private. They issue their own permits, so they're fair game. They're fair game. All right, these numbers and all, they don't ring true all the time because the new drawings show. I mean, they're not the working plans. They're not the approved. I can't show you. Never mind. Can't show you because the link is the link. I can show you. I can share you a separate link to each one, but I can't share it as part of my disclosure with getting the access to the disclosures. So I can't show you what I really meant. I can do it in separate videos, but if I click on it, it's going to show the site, the site that it gives you my private link into the site, and that'll get me in trouble with too many people banging it like that. They would be like, "What's going on here?" So that's the termination, or there's the access to. Just wanted to share about equilibrium, how this is all just, it was going to fail under creep, whether we like it or not. Whether we like it or not. Anybody got anything to say hello to? This is creep again. You can look up creep. There's a whole bunch of different creeps. Post-tensioning cables, they creep. I don't like post-tensioning. I'm not a post-tensioning man. I like it and I don't like it. I don't like it for its, at this time, I don't like it. For its willingness to want to fail. All right, Tom, Bruce, AS, anything before I roll out? So anyone come jumping into the video would be able to just enjoy it without me getting long-winded. And then on my other channel, I'm going to do Something about teeth, showing why teeth break. And this all goes in tying into the foundation stuff. Why teeth break with candy. Why they break with candy. And it's a structural thing. All right, so that's it. We're good. No questions. I don't even know how to get rid of this. Oh, over here. Google Hangouts. Take care. Wish you guys all the best. All the best.